One of the most impressive sights of recent years was the synchronized landing of the Falcon Heavy boosters. And although the center core didn't make it back simply because it didn't have enough ignition fluid to restart all three of the center core's engines, the overall mission was a success. But SpaceX wasn't the first to use this technique, and as we will see, there are several other ways to get launch assets back to Earth safely without just letting them burn up in the atmosphere. The maneuver which SpaceX use is known as a flyback, and it requires the perfect coordination of nitrogen cold gas thrusters, gimbaled engine burns, and the constant adjustment of the 4 grid fins, the heat-resistant control surfaces, to fine-tune the Falcon's flight path. The first stage of the Falcon 9 weighs more than 14 tons with empty fuel tanks, but it can fly with the greatest of precision to land safely from the edge of space. Separating from the second stage at hypersonic velocities and at an altitude of more than 70 kilometers, the Falcon 9 navigates through unpredictable, high-altitude atmospheric weather conditions to land at a precise spot on the Earth's surface. One other rocket can perform a similar feat, and that's New Shepard, a suborbital booster built by Jeff Bezos' Blue Origin. New Shepard is decorated with the image of a giant feather, which, according to Bezos, is a symbol of the perfection of flight. On November 23, 2015, New Shepard became the first rocket to fly to space and return to make a vertical landing. Less than a month later, on December 21, 2015, SpaceX's Falcon 9 became the first booster to launch a payload to orbit before returning also to land vertically. The age of reusable rockets had begun. But why did it take so long to see it happen? Landing a rocket presents some serious technical challenges, but the underlying reason for the delay has been the limited market for orbital launches. In the past, the launch industry was controlled by national and international space agencies. Even rich governments have often lacked the resources to fund innovation in space technology. Repeated launch failures of a government-funded prototype would usually result in the project being cancelled. And this is exactly what has happened to many of the 20th century's most brilliant machines that we often talk about on this channel. Jeff Bezos and Elon Musk have invested their personal fortunes into reusable boosters with the expectation that in reducing the cost of each launch, the market will grow. SpaceX and Blue Origin are filling a niche which has been left open by the national space agencies. But reusable space vehicles were a priority for NASA since the 1970s. However, once the space shuttle was selected, America was stuck with a design for a generation, and their gliding orbiter turned out to be hugely expensive and only grew more inefficient as it aged. On the other side of the Iron Curtain, there was a similar story. The Buran, the Soviet space shuttle, also became an all-consuming project that the USSR ultimately couldn't afford. But why did winged space planes do such a poor job of being what they were supposed to be, a reusable, affordable launch system? The inefficiency of the shuttle design can be traced back to the decision to carry a large set of wings and engines into orbit. The American space shuttle weighed 68 tons and the Buran weighed 62 tons, and both could deliver a payload of less than 30 tons to low Earth orbit. This meant that any payload delivered by the shuttle or Buran had to be lifted with a vehicle that tripled the total mass to orbit, and that was without the booster rockets and the fuel tanks and everything else required to get them there. Ironically, the extra weight of the crew quarters, wings and heat shielding also made the manned shuttle a dangerous way to get into orbit. For every ton you accelerate to orbital velocity, you then need to decelerate a ton of mass during re-entry through friction with the atmosphere. This process generates a lot of heat, and the heavier the vehicle, the more heat it creates. The shuttle and Buran dealt with this problem by being large and mostly hollow at the point of re-entry, increasing the surface area per ton for atmospheric braking. But another set of space planes reduced the aerodynamic pressures of re-entry by simply carrying less mass into orbit. Small space planes have been in development since the X-20 dinosaur first outlined in 1960, and 21st century robotic orbital vehicles can do more with less mass. Without the need for crew quarters or life support, they can carry an even more economical payload fraction. America has two high-profile robotic spaceplanes in development right now, the Boeing X-37 or Orbital Test Vehicle and the Sierra Nevada Corporation's Dream Chaser. Both of these launch vertically and then re-enter the atmosphere and glide to a horizontal runway landing. Not to be outdone, China is also working on a spaceplane called the Shenlong or Divine Dragon. Shenlong is aerodynamically similar to the X-37, but has only appeared so far as a scaled-down version for a 2007 drop test from a Chinese Air Force H-6 bomber. But while small space planes continue in slow development, reusable boosters have been studied for decades, sometimes adding a long-range flyback capability beyond anything possible with the Falcon 9 or the New Shepard. The second generation of the Energia program, that was the rocket which was to carry the Buran Soviet space shuttle, was codenamed Iagan or Hurricane, and was planned as a fully recoverable vertical takeoff and horizontal landing system. Like the original Energia rocket, Iagan would use strap-on boosters powered by the 4-chamber RD-170 engine. The RD-170 was ahead of its time and designed to ignite up to 10 times, and achieving up to 20 relights in tests. Soviet engineers realized that this relight capability made the Energia boosters suitable for reusability over many launches. When the Iagan's boosters separated from the main stage, they would unfold a set of wings to slow for re-entry, and then maneuver for a horizontal landing on a runway. The center core of the Iagan was also to be fitted with wings, a bit like the Buran, and this was to return to Earth using the same technique as the antipodal bomber, a design first proposed by Eugene Sanger in 1943. This would have the center core skip off the upper atmosphere around the globe until it returned back to its launch site, where it would then land like the Buran itself on a runway. Although the antipodal design was not followed up, the winged booster design was too good to abandon, and it reappeared after the fall of the Soviet Union as a proposed booster for the Angara system. The flyback booster was called Baikal and was essentially the same concept as the Iagan, fitted with folding wings and an air-breathing RD-33 jet engine for atmospheric flight. A similar system was also studied by the German Aerospace Center, the DLR, from 1999 to replace the expendable solid rocket boosters on the Ariane 5 launcher. Each liquid-fueled flyback booster, or LFBB, had forward canards, small rear wings and a turbofan engine, giving the booster all the aerodynamic capabilities of an aircraft. The LFBB design progressed as far as scale models before being cancelled, apparently because the hardware was becoming too large and complex to justify the economic savings. But ESA has recently funded a new reusable first-stage booster designed at Airbus to work with the upcoming Ariane 6 launcher. The Advanced Expendable Launcher with Innovative Engine Economy, or ADELINE, uses an unusual set of aerodynamic features to potentially achieve the most efficient and capable flyback yet. Once the first stage fuel is expended, ADELINE separates and re-enters the atmosphere, protected from the heat by the shield in the nose. Once in the denser part of the atmosphere, the booster uses wings and a pair of propellers to maneuver to a horizontal landing on a runway. Propellers can achieve even better efficiencies than jet engines, meaning that even less fuel needs to be reserved for the flyback. Now, something which SpaceX is doing is forcing the rest of the launch industry to re-examine their use of non-reusable launch systems. A few years ago, the Russian space agency, Roscosmos, said that they didn't see any point in developing reusable rockets. But after the recent success of SpaceX and their growing share of the market, Roscosmos now say they are actively looking at reusable rockets. So expect to see a lot more in the way of rockets and boosters flying back to base by themselves. So what do you think of SpaceX and Blue Origin's vision of a reusable future? Let me know what you think in the comments. I would also like to thank all of our patrons for their ongoing support, and you can find out more about that in the link now showing. And also, don't forget to check out some of our other videos too. So it just remains for me to say thanks for watching, and please subscribe, thumbs up and share.